one is to alert, right? So we all know the buzzer that people use to for doctors on call. Or we can use that to transmit information, or to confirm an action, or we can use that to delight people, just for game and fun. So for today, if you've been using like electrostatic displays and vibrotactile displays, you probably have been designing signals. And one question you may have is how many signals can you design that's distinct that people can use to map to different meanings? And so, in that sense, like today's talk might be helpful for you to provide something for you to think about. So, when we talk about haptics, most people don't realize how powerful haptics is as a channel for information transmission. So, I will start very briefly to give an introduction to information theory because that's how I think about how we estimate the quantitatively how much information we transfer through any sensory modality. But today, of course, we focus on touch. And I will introduce this concept of channel capacity and how we can work with that to maximize information transfer. And then I'll give an example of how we follow these principles, the way framework to design a successful tactile speech communication system. So I want to start with an existence proof with this photo. In the middle is my dear late advisor, Nat Dulac. He has normal sensory capability. He's having a three-way conversation with two gentlemen who are both blind and deaf. Okay, so they cannot see, they cannot hear. And the way they're having a conversation is by placing their hand on a talking face. And through the palm of their hand alone, they're able to get what the speaker is saying by monitoring the basically mechanical actions associated with speech production. And this method is called a teloma. The name came from two kids to whom the method was first introduced to. So they're called, the kids are called Tad and Oma. And they were the first two students in the US who learned this language, and they're both deaf and blind. So to show you how capable Tanama users can be, I want to go to the movies. Did you? So here you have an experimenter and you have a gentleman who's both blind and deaf, and then we also blindfold them and put headset phone on them to make sure that they cannot hear, they cannot see. And he has the hand on the speaker's face and he's repeating back what the speaker is saying. Enjoy the baseball game. The train leaves at 5 o'clock. They wanted to vote. Now, this next task is slightly harder. Instead of isolated sentences, this female participant is tracking a continuous paragraph. For all women. For all women. But not only that. But not only that. They wanted work in many trades. They wanted work in many trades and professions. And professions. To be open to women. To be open to women. And they wanted women. And they wanted women. To be paid. To be paid. The same as men. The same as men. For equal work. For equal work. You say it feels different. Now, the next one is free conversation. So the woman on the left is the experimenter, the gentleman on the right is deaf and blind. To listen to children? If children have words and they don't analyze, speak sometimes. Do you find it difficult to understand my Norwegian accent?
That is good.
So I hope you're convinced that I sort of played the video in full length. And I hope you're convinced that, you know, the sense of touch is quite powerful, right? Just through the palm of our hand alone, we are able to process something as complicated as speech. So I hope this convinces you that speech has a lot of haptics has a lot of potential that we have not tapped into. So put a number on how good it is. I have put 12 bits per second here. Now, if you're not familiar with the information transfer and all that, that's okay. I'm going to give a very brief primer, but I want you to remember this number because to me, there's been lots of publication of what the information rate is for sense of touch. They tend to be much, much higher than this number. And I would like to propose this number as an existence proof that people are actually able to achieve this, right? So it's 12 bits per second. So please remember this number. So let me make a little bit sense of what a bit is, just for you to appreciate, what 12 bits means in a second. So I will start with just this concept about information uncertainty. So this is just basic concept from information theory, and we use that as psychological concepts. So the definition of information is the reduction in uncertainty. And the condition for information transfer to occur is there needs to be uncertainty to begin with. And the amount of information is measured by the reduction in uncertainty. So we should talk about how we measure uncertainty to begin with. So I'll use this example of the number guessing game. If I tell you I'm thinking about the number one, you don't need to ask me a question to know what I'm thinking. But if I tell you I'm thinking about a number between one and two, you'll only need to ask me one question on average. And then if it's four numbers and you divide it into lower and half and upper half, and you ask one more question, you get it. So every time I double the number of digits I'm thinking about, it takes an additional one question. So you realize that, the number of numbers on the left and number of questions on the right are not linearly related. So that's something I want to impress on you. So this number of questions could be used as a measure of uncertainty, how uncertain you are in terms of what number I have in my head, right? So an intuitive measure of uncertainty, and bits, by the way, is the unit associated with uncertainty, is to define uncertainty as log base 2 of k, and k being number of equally likely outcomes. So if I have 8 numbers, it's 3 bits. If I have 2 numbers, that's 1 bit. And inversely, if I tell you there's a particular value of uncertainty, you can calculate the number of possible outcomes by raise 2 to the power of you, which is uncertainty. So I hope this at least fix some ideas that every time you increase information by 1 bit or you reduce uncertainty by 1 bit, actually the amount of number of outcomes it will like double. So by the time we get to 12 bits, it's like 2 raised the power of 12. And then we can transmit that much information in 1 second. So it's hugely impressive. Um, so to get to this number, information transfer and all that, we actually can run a psychophysical experiment called the absolute identification experiment. In this experiment, let's say we have k alternatives, and I'm using the piano as an example here. We randomly present one of the k stimuli at a time, and the task is for the participant to say, which key did I just press? The reason I'm using a piano to show this is to illustrate the following point. This is not to be confused with the discrimination experiment where I press the E, which is the green key, and F, and the orange dot key, and ask you which one is higher pitch, which one is lower pitch. If I ask you to do a discrimination by playing both keys, most people can tell which one has high pitch and which one has low pitch. What I'm running here is I'm only going to hit the key with a green dot. And I ask you, what is the key I just pressed? So this is sort of akin to people have absolute pitch. When you don't have a reference anymore, the task is so much harder. So information theory actually provides a framework for us to measure how well we can identify a signal without any reference point. And you would agree this is much harder. And the performance is more limited now by central mechanism memory rather than the peripheral sensibility resolution of our sensors. Um, to I'm just giving some background very quickly. To illustrate why we need to talk about information transfer instead of percent correct score, I have put data for four hypothetical experiments here. So experiment A is you have two stimulus alternatives. So this could be on an electrostatic display, it'll be like which one has the higher friction, right? Low friction, high friction. Or if you have a vibration, it's like which one has the higher amplitude or lower amplitude, or which one has the higher frequency, lower frequency. Basically, you have two signals, and R1 and R2 are the responses people give. And in the matrix, it's the number of times each stimulus is called each response. And here we assume R1 is the response for S1, R2 is the response for S2. If you only look at experiment A and B, I think you will agree that this participant is just hopeless, right? They're just confused all over the place. They cannot tell the difference between either the two signals in experiment A or the four signals in experiment B. And if you look at percent correct score and information transfer, and I do have an equation here, but we're not going to get into details. You just have to trust that I calculate everything correctly. So in experiment A, the percent correct score is 50%. In experiment B, the percent correct score is 25%. You may want to argue that the subject is just as confused in experiment B as in experiment A, right? They're basically not discriminating on any pair of stimuli. Now, if you calculate information transfer, nothing is being transmitted. So in this case, you can roughly think of information transfer as the correlation between stimulus and response. And then here it's just everything's confusing, right? But if you look at experiment C and D, you can see in experiment C, the participant is perfect. So it's 100% correct. In experiment D, the subject doesn't get anything right. The main diagnosis, all zero. So the subject is 0% correct. But in terms of information transfer, both come out to be 2 bits. So 2 raised to the power of 2 bits is 4 alternatives, right? We had a formula before. So when you use information transfer, we are looking at how well somebody can identify the identity of signal. So the difference between experiment C and D is that the participant got the labels all backwards. But otherwise, it's very clear. I think you agree with me. Even in experiment D, this participant is able to tell the difference among the four stimuli. So you can see percent correct score and information transfer kind of measure different things. So roughly for this lecture, for this purpose, it's like if you're transmitting speech, then how well can you tell the speech sound apart, right? You may attach wrong labels to it, but at least you can recognize these signals are different. So in some of our experiment, we actually use information transfer because that lets us get deeper into what is the information processing capability, how differentiable a set of signals are, how distinct they are. So if you run an experiment like this, so here there's a hypothetical data set. I'm plotting information transfer as a function of number of stimulus alternatives. And then this green line indicates how the experiment is going to proceed. So if I only present 2 stimuli, that's 1 bit, and most of the cases, people can do it perfectly. And then you increase to 3 alternatives, increase to 4, and at some point, the performance will plateau. And this is very universal. If you vary any particular physical variable and you look at how well people can identify them, so this could be the pitch of a sound, this could be the intensity of a vibration, this could be the level of friction. If you vary any one of them, eventually people saturate. And this is called channel capacity. And so I want to sort of impress upon you that this has nothing to do with the peripheral sensory resolution. It's how well we can remember how many things. So, like, if you think about a pitch of a sound, you can probably do seven, levels before you start to get confused. That's roughly the idea. So we actually know a little bit more about this. George Miller wrote a wonderful book called The Magic Number Seven, plus or minus two. And he looked at a lot of absolute identification experiments and came to the conclusion that channel capacity is usually within this range, 7 plus minus 2, for unit dimensional stimuli. So by unit dimensional, I mean you're varying only one physical variable, okay? And by the way, channel capacity for haptics tends to be towards the lower end. So the data I showed you is like five categories for the channel capacity, whereas for visual, it tends to be on the higher end. So you know that if you only vary one variable, you're not going to create a very high information display because you're just going to be limited by the 7 plus minus 2, right? So it follows that in order to achieve a high channel capacity, the stimuli need to have lots of dimensions. So going back to Tadalma, a talking face varies in mouth opening, cheek tension, airflow, laryngeal vibration. So it has many, many dimensions, so to speak. And if each dimension can carry 7 plus minus 2 number of signals. And then you combine all of them, all of a sudden it's a very rich display. So multi-sensory stimuli can code more information and they can lead to higher channel capacity. So in this sense, information theory provides a framework for us to combining, comparing, and assessing multi-sensory interfaces. So all of a sudden, if you're working on a friction display and somebody else is working on a vibrotactile display, you can discuss which display is transmitting more information in the common unit of bits. Whereas otherwise, how do you compare friction with, frequency, for example, right? So this is really helpful in terms of thinking about using a display to transmit information. So we actually did a project with Facebook, and they wanted us to build a communication system for English language. And first we did what everybody should do is literature review because we were trying to figure out what are the guidelines for maximizing information transfer. And so the answer turned out to be very simple. One is to use lots of perceptual dimensions. And I already said each dimension is limited to 7 plus minus 2. Therefore, you need to use lots of them. Um, and the other thing is don't use so many levels per dimension. Because if you have 7 levels of amplitude, 7 levels of frequency, and then you ask people what level is the amplitude, what level is the frequency, you mix them together, that gets very hard very quickly. So you want to use only 1 to 3 levels per dimension. So you either have high intensity, low intensity, high pitch, low pitch, and then you combine them, then this is the high intensity, low pitch signal. And you know what I'm saying? So all of a sudden you can transmit 4 signals with a combination of intensity and pitch. So that's the idea. And then you have another, sensory dimension you introduce. And then this is how you build up signals. The third one, which I won't have the time to go into a lot of details, but we discover through literature review is that illusory movements are really, really powerful. So this is like you may or may not know sensory saltation, apparent movement. This just means when you have a discrete array of vibrators, for example, by very carefully control the timing of how you turn signals on subsequent tactors, you can create this illusion of drawing a line on the body. And these are very powerful, salient signals that people can perceive very well, and you can use that to encode information as well. So here's my big data plot just to try to convince you, like, we basically summarize those principles from looking at this data plot. So let me explain what they are. We look at some 30 experiments where people measure information transfer, and we try to summarize them according to what we think are the key variables. In the end, we have two variables here. One is what we call the number of temporal and intensive dimensions. So we look at here, we convert it to number of bits, and we just look at like how many levels of intensities do you use? How many durations do you use if you vary duration? How many levels of frequency did you use? Remember the power of information theory. We can turn everything into bits. That's how we can compare apples and oranges and put them on one plot, right? So we try to summarize all these data. And then we pulled out another dimension, which I will call the number of tactors at different locations. So, with a vest, you can have lots of tactors and all that, and people think that's going to help you to transmit information. So we wanted to know how effective those are. So these are the data points. And then you have two colors here. The blue ones are the ones that involve movement illusion I just mentioned. Like, you turn a sequence of them on in a particular order, and they create this illusion of something moving on your arm, on your back. And red is just a signal at a particular location. You turn it on with some duration, frequency, amplitude, and all that. Okay. So to begin with, let's look at only red dots, and let's only look at the top dot. So for example, here, we don't care about the lower information transfer. We just look at the tip of these red squares. And I think you agree that as we increase this number from 1, 2, 3, 4, all the way up to 24, you would agree that we're actually not gaining a whole lot in information transfer. So using a lot of tactors from information transmission point of view is actually not that helpful. Location is not that useful a piece of information. But if we look here, we can see that as you move from lower dimension to higher dimension, numbers do tend to increase. So the record holder used to be me, but somebody has broken that already. But I held it for just about 20 years, as far as I can tell. So this is like 6.5 bits. Is what I have measured with my PhD thesis work. So I have a little note that says 2 raised to the power of 6.5 bits is 90 stimulus alternatives, which means when I ran those experiments, I was able to identify 90 signals without mistake. How did I do that? Right? So the device is a 3-channel device, which you couldn't see in the top because it's in a box. But essentially, I have 3 motors that can move 3 fingers, thumb, index, and middle finger. And these are very wide bandwidth motors, so I can move them very slowly like this, or I can deliver vibration or any frequency in between. So the bandwidth from 0 to about 300 hertz. So I used a lot of features such as duration of the signal, amplitude of movements, frequency of movements, and then I combine them so that I'm like, okay, this is a 300 hertz smooth vibration. coupled with a 2 hertz, movement. Plus, there's a little bit of roughness to it. So that's probably another 30 hertz modulation on top of it. And this is how I'm able to identify it by noticing the components that goes with it. With sufficient training, you can sort of learn these things. Um, so now let's go to the blue circles. This study here by my former student, so I cannot be too mad at him for breaking my record, got 7.02 bits. Now, 6.5 to 7.02 does not appear to be a huge difference, but remember, every time you increase 1 bit, it's a doubling of number of stimuli, right? So if you look at the note I have put here, 2 to the power of 7.0 is 128 signals. So what did they do? They took a phone, they put 4 vibrators on there. So now they can turn on just one, they can turn on two, they can turn on three. And furthermore, because this is a blue circle, they also use movement illusion. So now you can feel signal between A and B. And maybe it's like A, B, and a D. So like you feel half of it, maybe it forms a whole circle. So you can imagine this is how number of signal gets created. And then you test how well people can recognize these signals, right? So the point here I want to make is that once you have these movement signals, your information transfer can go even further. So this is just a very superficial description of the data we collect, our literature review and how we decided to approach the project. So let me move on to this project we did and show just a few details. So from June 2017 to June 2018, which is about 12 months, that's all the time we had from Facebook. They funded the project. We had a team of 9 researchers at MIT and Purdue set out to create a tactile communication system. I want to emphasize that this was not for people with disabilities. The idea is that if you send somebody a text message, you receive it with a tactile display. So the question is, can you do this? And within 12 months, can you build it? And can you actually run human study to prove that people can do whatever it is that you set out to do? So in our case, TAPS is the tactile phonemic sleeve. We made a decision to encode phonemes, and we had 24 tactors worn over both sides of the forearm. And then we encoded 39 distinct haptic signals that maps to English phonemes. We ran through more than 100 participants. We trained them, we tested them to refine the signal, and we meticulously tracked every minute they spent learning because we also cared not just how much they can learn to communicate with this device, but how quickly they can learn to do so. So I'm very proud to say that the best participants acquired up to 500 English words at a rate of 1 word per minute. So I'm going to show you a plot before the end to show you how much they can learn in 500 minutes. Okay. Now, let me show a video first to show you what the device looks like. I'm not sure you can see anything, can you?
Yes, it's just fine. We can see perfect.
Okay,
Yeah,
okay.
that's great. Thank you. How
Okay.
many actuators did you have on the sleeve?
24.
24. Okay, perfect. Thank you.
One, two. So, bro, me,
So I hope you're convinced that, he can do this. The way this works is that because we're encoding phoneme, so for something like a moose, you'll feel mu, oo, I'm sort of animating on my arm, and then you have to put it together in your head. It's like a moose. Oh, that's moose. So this way, we tested 500 words eventually, but I think you would agree that this could be extended to even a larger vocabulary. It's just we need to use fixed number of vocabulary in order to do data collection. Oops, I didn't mean to. Yeah. So I want to show you very quickly, Professor Berlinghurst asked how many tactors. I think that's, we made a lot of quick decisions because we didn't have the time to run careful experiments. So it may seem like 24 just pulled a number out of hat, but we had some intuition. So I want to sort of justify that a bit. So remember on the left here, I gave 3 guidelines, right? Use lots of dimensions, very few levels per dimension, and use illusory movements. So on the tactile phonemic sleeve, we try to recruit as many dimensions as possible. We had 24 tactors, so we obviously used the location, but very quickly we realized you can't identify 24 tactors on the arm. But what we can do is we can roughly tell it's the wrist, it's the elbow, and it's somewhere in between. So on the dorsal side, you have 3 locations, and on the volar side, you have 3 locations. So we actually had a total of 6 locations, but we had 24 tactors. Why did we have so many? We If we put multiple tactics in a cluster, we were able to use spatial summation to try to get a bigger dynamic range of the range of intensity we can achieve. So that's why we use multiple per location. But the location is really 6, just so you're aware. We did not use more than one level of amplitude. This may be very counterintuitive because that's the first thing everybody does. But in the video, you saw that Jay Hong was putting the sleeve on his arm. Every time you do this, obviously there's variation, how tight, how loose you do this. And then of course, how much, the tactile is compressed against your skin. So we found that people could not even reliably identify high amplitude versus low amplitude, high intensity versus low. So we just had one level. So this may come very shocking, but given the construction of the system, that was the best we can do. We definitely use frequency. We use the voice coil kind of tactor, so we can use low frequency and high frequency. And we use duration, and I tell you a bit more. And we use the waveform modulation to create this heavier sensation. Again, I'll tell you why we did it that way. Few levels per dimension. So for each of these dimensions, we use no more than 2 to 3 levels per dimension. And then we use lots of illusory movements. Now, here comes how we encoded this, because the success depends on how quickly people can learn the association between signal and 39 phonemes, and also how well they can memorize it, right? So they remember we collect data over 500 minutes. We didn't make people sit for 500 minutes because you'll just get fatigued. Instead, they only come into the lab for 10 to 20 minutes a day. So this is like actually like taking advantage of memory consolidation and all that. So they have to remember what they learned. So I just want to give some example. To begin with, for the 15 vowels, they all involve movement. And for the 24 consonants, they're all based on location. So right away, if a signal moved, it's a vowel. If it didn't move, it's a consonant. Once I tell you this, and end of story. You'll never get confused again, right? And the reason we make vowels move because movement tends to take longer, and vowels do take longer than consonants. So when we designed these mapping, we thought a lot about the feature of language and how you convey that in a way that people can remember. I'll give one more example. The front of the wrist is mapped to the front of the mouth. We explain to participants. The elbow represents the back of your mouth. So if I play the same signal at the wrist and elbow, I tell you one is p, one is g, was k. you get it because you know where the sound is. So this is what, by the way, we use a lot of international speakers. It turns out they know the location of the sound. They know what phoneme means, because we have some concerns like, do they have to be native speaker? No, they don't have to be. Let me jump to the conclusion. So I promised I was going to show you the learning data plot. So here I'm plotting equivalent number of words learned from 0 to 500 as a function of cumulative learning time, which is from 0 to 500 minute. So this red line represents a rate of 1 word per minute. Okay. And then we had 10 participants. I don't know. Yeah, roughly 10. So the study goes like this. First few days you come in, you learn the consonants, you learn a few vowel until you have learned all 39. So you're not really doing any words. But then we give you a vocabulary of 10, we give you a vocabulary of 20. So we had to have one measure to indicate your progress. And the way we do this is we take the vocabulary size and multiply it by the correct percent correct score. So we use that to say this is the number of words you have learned. So then we can sort of plot this out regardless of how large the vocabulary size is. And then you can see that for some of the participants, they were actually learning faster than 1 word per minute. Some of them came very close. And then the rest of them didn't do so great. And that's just to be expected. Again, we were just looking to see if anybody can do it at all, right? It's just like a language. It's hard for some people, but it's easier for other people. The ones who do really well really view this as a game. They're like coming every day. They're just trying to, they find it really fun. And this is only useful if you actually can do this for communication. So during pandemic, we actually ran experiment with these two students. They're both very well trained. So they would type a message. So Gina could type a message on her keyboard. Jaehoon will get it on his left arm and he'll try to make sense of it. And he'll type another message back, which Gina will receive on her left arm. So this is, and then we collected how they communicated. So this is all open vocabulary. They did agree on a topic to begin with. Otherwise, it's just way too hard. But otherwise, it's not pre-rehearsed. So just want to acknowledge all the people who participate in this at Purdue, MIT, and also Facebook collaborators. They funded the research, but they also participate in a lot of the discussions. So I want to conclude by saying that Tadoma method demonstrates an information rate of 12 bits per second, but the highest reported information transfer is only 7 bits. And actually, it's really hard to measure rate. So we don't even have a rate. But that's a huge discrepancy, right, between the two numbers. So we've yet to match the information transmission potential of touch. I like to say that we don't quite know how to talk to touch. We tend to use image, or we think of it as spectral analysis, but touch is neither. It has its own property. So we need to continue to figure out how to transmit information effectively. And then I want to sort of leave you with the do's and don'ts for high information transfer when you go back to your haptic displays you work on. One is to use lots of dimensions, whatever physical variable you can vary, use them, but don't use more than 2 or 3 values per dimension. So in our case, we had 3 locations, but that was the only variable that had 3 levels. Every other variable had 2 levels, for example. And then do learn about movement illusions because they're very powerful and salient in encoding information. So with that, I thank you for your attention and the interest. I'm happy to take some questions.